Hello, everyone. Welcome to the second episode of the Modifying Plants vs. Zombies with a DLL through DLL injection series. This is the second episode, and in this episode, we're going to be completing the mod on a very bare bones level. And a list of the tools that we're going to need this episode are Cheat Engine and obviously Visual Studio, which we should have from the previous episode, and a new tool this time, which is Reclass. I have heard a lot of comments from you guys saying that the pace of the previous episode was too slow, so feel free to run this episode on 2x speed if you think that it's too slow. But also, I have kind of cut down a little bit on the yapping. And even when I didn't, I kind of put them in their own sections. So we're going to first start by learning a little bit about data structures theoretically. So if you already know what data structures are, feel free to jump to the practical version of data structures. And then we're going to be learning about code injection theoretically again, which is just a bunch of yapping so that we understand what we are going to do. And again, if you already know what code injection is and how it works, then just straight up skip to the practical section. So yeah, I hope you guys enjoyed the video. Without further ado, here we go. Okay, so now let's talk about data structures. So what are data structures? Data structures are essentially the computer's way of representing entities, right? So obviously the computer has a memory, and everything in that memory, everything in the game of Plants vs. Zombies has to be somewhere in this memory. So the health of plants, where the plants are planted, on which lane, on which column, etc., what type they are, if they're walnut, if they're sunflower, etc. All of this has to be stored somewhere in the memory. Now the question is, how does the game know, for example, this is the health of the walnut, this is the health of the pea shooter in the X lane, in the Y column, etc.? How does it know that? Well, it knows this through data structures, right? Because like we said, it represents entities, right? So how does it do this? Well, essentially, it allocates a region of memory and says, okay, so let's say we have three plants, say plant A, plant B, and plant C. Here, so we have plant A, plant B, and plant C. So the game basically says, okay, so this entire region of memory is going to be reserved to plant A. Everything that has to do with plant A is going to be somewhere here, right? So essentially, what is the data structure? The data structure is stored here. However, the data structure is essentially a way, like a dictionary, right? So here, let's assume that this is the plant data structure. Obviously, this is an example data structures, don't use that. And here it tells us that the health of the plant is +4, right? Now, what does that mean? Well, if we know that plant A starts here, if it is here, then we just move 4 bytes from its starting position. So instead of accessing this, for example, we would just move 4 bytes and we'd access this instead. Now, you will notice here that they're all increments of 4. Now, why is this? Usually, just know that as a rule, since Plants vs. Zombies is a 32-bit game, it's going to be in 32-bit increments, which is 4 bytes. So it's just going to keep adding 4 bytes each field. Now, this pattern will be broken in some cases, and we will see this practically in a bit. But for now, we need to understand what data structures generally are, and they're basically just like a dictionary to access different attributes that belong to the same entity. So if we want to access the maximum health of plant A, and we know that plant A starts at 0, then we would just add 0 to the offset of the field max health, which is 8. Excuse my terrible handwriting, I'm using a mouse. So we would go 4 bytes, 8 bytes, and there it is. So this is the maximum health of plant A. What if we wanted the health of plant C? Well, we know that plant C starts at 200. So we would simply go to 200 plus 4, which is the offset, so 204, and this is the health of plant C. So these are data structures. Obviously, we will have to reverse this ourselves. We would have to know where the health is located from the position of the plant. We'd have to know where the max health is. We have to know where the timer is, etc., etc. So we're going to go ahead and reverse the plant's data structure practically in a bit, and we're just going to figure out where everything is using Reclass and Cheat Engine. Okay, so here I have skipped to basically a normal game, and we're going to be using a walnut to find the health address like we did in the previous episode. So a little bit of digging would make you realize that a walnut has pretty much 4,000 HP, just through a quick look at the wiki. So let's go ahead and plant our walnut. Okay, so here we know that the health of the walnut is 4,000. So let's go ahead and scan for 4,000. And then, once the zombie actually takes a bite, we don't know what the health value is, but we definitely know that it has decreased. So we're going to do this. We're going to click next. And thankfully, there's only one address right here. So let's just confirm that if we resume the game, it does in fact get lower each bite. So what we need to do now is we need to find out what accesses this address. And the reason as to why we need to do this is because we want to find out where the health is in the walnut's data structure, and we need to find out where the walnut itself is so we can mess around with the other things using Reclass, which I will start up soon. So here, yes, and now let's resume the game because obviously nothing's going to access the health unless it's running. So here we see a bunch of codes, and obviously we're not gonna need all of them. We really just need one. So which one is it? Well, here we can see there are two ones that we are actually interested in. The ones that compare it to 0. So here you can see it compares, which is CMP stands for compare, compares the health, which is this, to 0. Now, why would we be interested in what compares it to 0, you might ask? Well, because essentially we want a code that runs only when the game is resumed, not when it's paused, so that we can basically, once the game checks for the health, we can just decrement it passively. So we can inject our code that decrements the health there. So let's go ahead and click Show Disassembler right here. So here we can see that it basically it compares it to 0, and then if it's not equal to 0, so here if we expand this here, it says jump if not less, right? So what does this mean? Here it means it compares it to 0, and here it says skip this if it is not less, right? So if it is greater or equal. So if it is greater than 0 or equal to 0, then just go straight here and skip this call, right? Now, there's also another thing that we can notice here. What does this compare? Well, it compares EBX plus 40. Now, if you remember our little presentation about data structures, clearly the position of the plant is in EBX and the offset of health is 40. So this is a very crucial bit of information. So what we're going to do is we're going to set a breakpoint right there, and we're going to resume the game. And breakpoints basically pause the game when the code reaches this point so that we can take a look at all the registers and change the code or the register values if we so like. And what I'm going to do here is I'm simply going to take the value of EBX, which we know from here contains the plant, and I'm going to put that into Reclass. So I'll leave the link to Reclass in the description, obviously, but very important detail here is you need to open x86, not x64, like we mentioned in the previous episode. So we're going to start up Reclass, and we're going to hit File, Attach to Process. Obviously, we want Plants vs. Zombies, so here it is, attached to process. And the first thing you need to do is you need to put the address of the plant right here. So we're going to paste the address here, and there it is. Now, we also need to add a couple bytes just so that we can have more space to look into the plant. So let's go ahead, and we already know where the health is. So here we know that the health is EBX plus 40. So we're going to go to 40, 40, 40. There it is. And you can clearly see it right there. It's 3,580. So we're going to declare this as an integer, which should be right here. There it is in 32, right? And we're going to call this health. Right, so now we know where the health is. Now, just by looking, we can clearly tell this is the maximum health, right? It's right next to health, and it has 4,000. It ticks all the boxes, so it must be max health. Hold on. Okay, so now we know where the health and the max health is in the plant data structure. Now, here's a question that you might ask. Do we need to know everything in the plant's data structure before we can actually use it? The answer is no, you don't. You just need to know what you need to know, and that's really it. So, let's go ahead and you can then now remove the breakpoint because we no longer need it. We now have obtained the plant's address. We're going to continue the rest in Reclass. So, here we can clearly tell if we change this, actually let's not change this. How about we change the maximum health instead? So we make the maximum health 10 times what it's supposed to be. We can clearly see that despite the walnuts still being healthy, it has immediately went to its final state because it thinks it's at 10% of its HP, which is technically true, right? So let's fiddle around with the other things here so that we can maybe start to get a clue of what the other fields are. Now, there's another thing that we can very clearly find out here, which is the lane and column at which the plant is planted. So let's count the lane and the column. So the lane here this is 0, this is 1, 2, 3, and 4. So let's look for 4s here. This is a 4, so we can reasonably assume that it is the lane, right? So let's go ahead and say, wait, my bad. Here, call this lane. Now let's change this to make sure that it is a lane. So we can see that the walnut actually does not switch lanes, but we can clearly see that the zombie does ignore it unless it's 4. And the reason behind that is the X position of the walnut has not been changed. So still on the same place of the screen, but in the game's memory, it actually thinks that the walnut is right here, right? So we can conclude that this is in fact the lane. We can also find out the colon pretty easily. So this is 0, this is 1, 2, 3, 4, 5, 6, and 7. So let's look for a 7. There it is. We can then reasonably conclude that this is the column. Now, there is not a very easy way to prove that this is the column from my experience. If you change this, not much is going to come out of it. Now, there is another thing here that we can also notice is that these two numbers look very suspicious. So let's go ahead and change them to find out what they are, right? So let me put Reclass and Plants vs. Zombies next to each other, and this is basically just going to be some tinkering around, and obviously you don't have to tinker around, you can just disassemble the game, but we will figure this out next episode. Tinkering around for now is just the easiest, most simple method. So let's change this to, let's say, 500. We can clearly see that the walnut's X position has actually moved. And there you have it, right? So the walnut's X position has actually moved, so this must be the X position, right? Now this, by natural progression, should also be the Y position, so let's just make sure, and there it is. But as we have learned from changing the lane, the Y position on the screen doesn't actually matter, it's the lane that matters. So these are cool and all, but how exactly do we actually use them? Well, first of all, let's call this the plant. This is the plant class, right? Now, let's actually bring this into Visual Studio. We want to bring this data into Visual Studio so that we can actually start changing the health of stuff. So how do we do this? Well, we right-click and we click Show C++ Code of Class. And here, obviously, this code is going to change the more that we figure out, but basically, this is what you need to do. So we now have the plants class. And in case you don't want to do this tinkering, even though it's very fun, and I very much advise you to do it, I will leave the fully reversed plant class in the description for you to use basically for free. So go ahead and copy that But if you don't want to copy that, then you can just tinker around with the plant and make sure to not cross over to the next plant, because plants are in fact put next to each other in the memory. So you might actually go too down that you actually start editing the next plant, not this walnut. So yeah, I will now start Visual Studio and put this code in there. I'll see you there. Okay, so now let's talk a little bit about code injection. What we did last time was not code injection, it was instruction overwriting. So instruction overwriting is a little bit different because here the game's code was something like sub ESI EBX. It subtracted EBX from ESI, etc. Right? And this obviously corresponds in the game memory to some combination of bytes, right? So what we did was we changed one of these bytes to something different. In this case, we changed 29 to 01, which changed it from a subtraction instruction to an addition instruction. Now, this is very simple. However, what if we wanted to add extra code? So what if instead of changing this from a sub to an add, we wanted to start writing our own code and doing things that, don't exist? Well, in that case, we're going to have to resort to code injection because we can't just simply fit code in here in this region of memory that simply just doesn't fit in it. That's not how memory works, and this is for a couple of reasons that I will now explain. So here, let's assume that this is the hook point. We want to put our new code that is right here in this hook point, like right after this code, right? Now, how would we do that? Well, you would think that, okay, maybe we can just create new space, like we can alleviate space, move the memory around and do this, and then we can put our own code in here like so. Now, this is a hassle for a few couple reasons. The first reason is because if we do that, we're gonna have to shift over every single one of these bytes over and over and over and over and so on, like so. But we don't want to do that. This is too much work, for one, and for two, it's still not going to work. This is because of something that we like to call relative jumps. So what are relative jumps? Well, relative jumps are basically, let's assume that in the game code here, at this point, there is a function, or like there is a function call, right? It calls the function that is right here, or it jumps to the code that is right here. Now, what if we insert our new code in there? Well, if we do that, we are going to basically move this around like so, and then we're gonna put our new code in there and put this back like that. And then this is going to make the jump end up somewhere completely different. It was not supposed to go, it was supposed to go somewhere here, right? So that is just not going to work either. It's going to break the game in a lot of ways. So we can't do that. Well, what is the solution then? Okay, so let's assume that the code that is at this particular point is this subtraction instruction, right? So what are we going to do? Well, what we can do is we can essentially take a copy of this code and we can change this code to jump to our new code, right? So what it's going to do then is once the execution reaches this point, it is instead going to go straight to our code, right? So it's going to go to our code and is going to start executing our code. And then what we're going to do here is we're going to add a little bit of code to the end of our code, which is the original code that used to exist there, and also another jump back, right? Um, so a jump back instruction. So this is going to make our code basically go all the way back to right here, right? So it's just going to go back to where it was supposed to be. It is essentially as if we have moved this entire segment of code and put our own without any of the downsides of doing this. So this is essentially what code injection is. Now, of course, this is very simple theoretically, but practically it becomes a little bit more difficult, and we will see how this works and how we can properly inject code in a minute. Okay, so now we have yapped enough, it's about time that we get into the actual practical code injection. So before we begin, let's first take a look at our project once more. You will notice that there are two new things here. First of all, there's the hook function, and second of all, there is the plant class that we have just reversed. Now, there is a possibility that it's going to put red lines under an int32t, telling you that it doesn't know what that is. And if that's the case, just put an include cstd int at the top, and that should solve the problem. So this is the plant class that we have reversed. If you have reversed more fields or attributes, there will be more attributes here, and that's totally fine. And you will see this particular hook function. Right, now this hook function, I will not go into too much detail in it, but there is a very good video. Oh my god, it's not responding. There's a very good video about this hook function that if you want to know details about, I will leave the link for that in the description. That is, of course, in case you want to actually know in depth what this hook function does. But if you don't want to, then just know that basically what it does is basically just this. It just, you give it an address and you give it a function, or so you give it an address and you give it a function, and it just makes the address, the code at the given address, so this here, at the hook point, basically just jump to our function. And that is all that it does, right? So, here, first things first, we need to find out where we're going to make the hook, right? So going back to our code, here we remember that this piece of code is what compares the health to 0, right? Now, here's a hint. Hooks basically take up 5 bytes of space. And here, this takes up 1, 2, 3, 4 bytes of space. So there are two options that we have here. We can either take two instructions, or we can just take the call instruction that's right before it, and it takes exactly 5 bytes, which is exactly what we need. By the way, each two letters are a byte, in case you did not know that. What we want to do is we want to hook here instead. This is so much more convenient than hooking on these particular, you know, replacing two instructions is more difficult than replacing one instruction. Now, that's not to say that replacing two is impossible. You can still hook here if you so want, but for the sake of making it easier, I'm going to hook right here. And in the next episode, we're maybe going to hook at a little bit of a more unconventional place. So the first thing that we need to do is, like I explained here, is we need to save the old code. So here, this old code just calls this function. So let's go ahead and save this function, right? So I'm going to make a constant d word, and that's going to be the old function, right? So we're gonna put 0x, of course, because that's just how Cheat Engine and Visual Studio work. And that is the first step. So saving the old code is the first step. The second step is finding out where we are gonna make the hook. So the hook here, we're gonna press go to address, and we're just gonna copy that. Const dword hook point. We're gonna put that. And by the way, you can remove these first two zeros. It's essentially like saying 001. It's the same value as 1, so you don't need the first two zeros. And then what's next, right? So we know where we want to make the hook, and we know what the old code does. So all we really need to do now is just make the function that's going to take the place, right? So let's make the function here, void std call damage plant, right? And you need this std call, by the way. This is very, very crucial. So what you need to do, obviously damage plant is going to take a plant pointer, right? So we're going to say plant pointer, my plant, I guess, right? And here's the thing. This plant is actually the plant class that you have reversed right here, right? This is basically you, since you have the data structure of the plant, you have basically told your DLL, okay, so this is how the plant class is structured. This is how it's laid out. So this is why it knows what a plant is. So the more fields that you know, the more things that you're going to be able to manipulate, etc. Right? So here, what we want to do here is every time this function is called, we want to take a plant, and obviously we want to damage that plant. So how are we going to do that? We just say my plant, we click dot, and obviously health. And once you click health, is going to turn into a, the dot is going to turn into this arrow. The reasoning behind that is because it's a pointer, not a class itself, and I might make a video explaining the difference between class pointers and just regular classes. But for now, just know that, this is what you need to do. Now, minus minus basically means decrement it by 1. You can also say minus equals 1 or 2 if you want to make it go down faster, or you could also say equals my plant dot health minus 1. So you're essentially saying it equals itself minus 1. This is just basic C++. I'm just going to keep it at minus minus. So now this is the entire function that we want to do. We then need a handler function, a function that's going to handle, that's going to basically be the middleman between assembly and C++. So here we know that the plant is obviously in EBX, right? But how do we tell this to this function? How do we tell it that my plant is in EBX? Well, we need another function that's going to be basically the middleman between these two functions. And it's going to tell it, okay, the plant is in EBX, right? So here's what we're going to do. We're going to do void decal spec naked, and then we're going to call the function, say, middleman, right? And that's all you need to do. Now, we want to write assembly. So basically, because we want to write assembly in this function, we have to make this function a naked function. So the compiler is not going to add any of its junk. It's just going to be exactly what we write in here. And because of this, we have to deal with the fact that we can't really have any parameters. We can't really deal with any variables, etc. So it makes it a little bit more difficult. But since we just want this as a middleman function that just routes it to this function and tells it where the plant is, we don't need to do that. So in order to write assembly, just do this, and here is an ASM tag. So now ask yourself, where is the plant? Well, we know that the plant is in EBX, so we're just going to go ahead and push EBX, and pushing EBX is basically giving this function the last parameter. If you push again, we're going to give it the parameter before the last, and a third time the parameter before the last, right? But this function only takes one parameter, so we're just going to need to push that one parameter, which is my plant, or the plant that's in EBX. Then we need to call the function. So we're going to say damage plant. And this is basically what you need to do to route the function there. However, that's not it, because because now we have called our function. We have yet to call the original function, so we have yet to restore the original code, like we said we should here, and we have also yet to go back to here. So we need to not only restore the original code as shown in the first line, but we also need to jump back to where we're supposed to be. So first things first, let's restore the original code. So the original code is basically this, right? It's call the old function. So we're going to call old function just like that. And then we need to jump back here, right? Since we're going to hook here, we're going to jump back here. So we're going to go to the address, going to copy this. We're going to just make another D word here. We're going to call this jump back, right? Again, you can remove those first two zeros. It doesn't matter if you do or not. And once we have executed the old code, we can just jump back, and that's it. So we have pushed EBX, or basically told this function where the plant is, and then we have called the function. Then this is the old code. We have basically created the old code that was once here. And once we have done that, we have basically just jumped back to the next instruction. So we have essentially inserted this piece of code into here, without, of course, moving the code, shifting the code, and causing all of these issues. So these are the functions that we're going to need. Now, what about the actual hooking part? Well, we're obviously going to need to call the hook function. So we're going to call it, right? And we first need to give it the address. Well, the hook point is right here, so we're just going to give it the hook point. And then we need to give it the function. Now here's a question for you. Are we going to give it damage plant, or are we going to give it the middleman that connects it between the assembly and the damage plant? Well, if you have been understanding what I've been saying correctly, you would guess the middleman, and that would be correct. And there you have it. That's literally all we need to do. So let's go ahead and build this project. Okay, so now all we need to do is just build this project. Where is it? Build solution. There it is. Or just Control B. And then, once it's done building, there it is. Build one succeeded. Okay, so now that we have that, we can just, okay, we're already in Plants vs. Zombies, so now we can just press Tools, Inject DLL, and you will see here, this call is going to now change, right? So let's press Open, and no. Okay, and as you can see, it now jumps to passive damage.middleman, which is our code, our injected code. So now, if we go back to the game, let's put a potato mine right there. Its health should passively decrease, and there it is, just like that. So obviously, this goes out too quickly, even though we are only negating it by 1. But the next episode, we're going to focus more on balancing this mod out. So what if we want to decrease it by less than 1? But this health here is obviously an integer. We can't decrease it by a float value. So how can we do this? All that and a little bit of reverse engineering is going to be included in the next episode, so stay tuned for that. But for now, we have basically made a very, very simple mod. Of course, you can also do some other cool stuff, such as, for example, saying my plant dot x position equals 0, my plant dot, I don't know, y position equals what's the 300, right? And then you can build, and of course it's not going to be able to build because we still have the game running. So I'm just going to do this and restart the game, and then since we didn't inject, it should be able to build. There it is. And okay, there we go. Inject the passive damage, okay. And then I'm just going to make this a little bit faster for you guys. Okay. Right, so here, there you have it, right? Let me reduce the speed now again. You can change the X position and the Y position since we have reversed those attributes of the plant's class, right? And so that's really all there is to it. So yeah, that's going to be the end of this episode. Hope you guys have enjoyed. Hope you've learned something new. And I hope you have fun tinkering with the plant class. But if you don't want to do that, of course, I will leave the entire plant class in the description for you to use if you so want. So yeah, that's it for this episode. Hope you guys have enjoyed, and I'll see you guys next time.